Hello, my name is Alina Pereira, and I'm a student at the University of Texas at Tyler. And today I'll be presenting on my project, a wearable multiplex sensor for real-time and in-situ monitoring of wound biomarkers, instructed by Dr. Shawana Tabassum. I would like to start off by introducing the concept of chronic wounds, which are nothing but wounds that fail to go through the normal phases of healing in an orderly and timely manner. Around 2% of all hospitalized patients worldwide have a chronic wound. In addition, 70% of these wounds recur, and 34% are accompanied by infection. Mostly affects the elderly population, since with aging, our immune system becomes weaker and it becomes slower and less effective. The process of treating such wounds can be time and supply consuming, and that is where the smart patches come in. In this figure, we can see on the top portion some examples of traditional treatments that we have had for years and years, such as wound management, which is made through applying the patches on the wound site, applying drugs manually, and having multiple medical devices fixated on the wound site. On the bottom portion of this figure, we can see some of the advantages which are offered by the smart patches, such as biocompatible skin adhesion, smart feedback therapy, which is nothing but drugs being liberated on demand, and real-time health monitoring of the wound condition. The smart patches work, the way that they function is basically having a flexible electronic, which is responsible for gathering this data and sending it to another device, and the biosensors, which are responsible for capturing this data and sending it to the flexible electronic. Nowadays, the current smart patches are able to detect components such as uric acid, pH, and temperature, for example. Now, the question is, how can we offer a better proposal than what already exists in the market? That is where our work comes in. We decided to implement a 4-in-1 smart patch. But what does that actually mean? When breaking down this concept, we're referring to 4 biomarkers in a single device, where biomarkers are molecules present in bodily fluids such as blood, which work as indicators of normal or abnormal processes in a condition or a disease. The biomarkers we decided to implement in this project were pH in its alkaline state, interleukin 6 or IL-6, interleukin 1 beta or IL-1 beta, and C-reactive protein or CRP. These 3 components, IL-6 and IL-1 beta, which are cytokines, and CRP, which is an acute phase protein, are present in the wound site in elevated levels when an infection occurs. With that in mind, we decided to include these protein biomarkers since they have not been included in previously reported research projects for smart wound patches. And here's a demonstration of how our biosensor would be applied on a wound site. It would be attached to a medical gauge and connected to an analyzer via wires. The process we followed to come up with our biosensor was having a screen-printed electrode, or simply SPE, with 4 working electrodes, each one of them to capture a different biomarker, a counter electrode, and a reference electrode, which altogether compose a 3-base electrode system. SPE is the most cost-effective way of producing electrodes nowadays. After having this designed, it was sent to, after having it designed in AutoCAD, it was sent to a benchtop precision cutter. The flow of procedure we followed in order to come up with our SPE was to first have the bare SPE formed, second, applying a liquid graphene paste in all of the electrodes but the reference electrode. Then having a silver paste applied only on the reference electrode. And finally, having 4 different coatings applied on one of the working electrodes. Our first chosen biomarker to be evaluated was CRP. And this is how we conducted our electrochemical tests. First of all, we attached some copper tapes to each one of our electrodes. And after doing so, we applied a liquid CRP solution, which englobed all 3 electrodes at once. After this connection was made and stabilized, we connected alligator clips to the copper tapes, which were then interfaced with the potentiostat responsible for analyzing this data and processing it, and then sending it to the PS Trace software, which is responsible for gathering and plotting the signals. How will we get conclusive results from this? Well, here is how we conducted our tests. We decided to evaluate current in order to prove that there are detectable CRP concentration levels in our solution. But why current? Well, we found out from observing this graph that as our concentration of CRP increased, our current peaks started to decrease, which shows that current is inversely proportional to CRP. The concentration range we chose started from 0.08 milligrams per liter up until 120 milligrams per liter, which falls within the range of the CRP cutoff level, which is 8 milligrams per liter, considered to be a normal clinical condition in wounds. The technique chosen for our project was cyclic voltammetry, which consists of having the y-axis as current and the x-axis as potential. It is a scan which reaches a reduction peak and an oxidation peak. In order to analyze this, 3 readings were taken with an interval of 2 minutes between each one of them. And these are the figures of merit we were able to gather for our project, where sensitivity is the ability of method to differentiate between 2 close concentrations, and ours was found to be 1.194 microamperes per milligrams per liter of CRP per centimeter squared of working electrode area. The limit of detection is the closest differentiable value closer to 0, and ours was found to be 5.8 milligrams per liter. The cost of producing our sensor, including all 4 working electrodes, was $46.17. In order to demonstrate that our sensor was capable of detecting CRP concentration levels, regardless of the presence of interfering species, we conducted a selectivity test. And from this plot, we can observe that the current difference levels for both concentrations of CRP are higher than when there were only interference present. Another important feature was to understand if our sensor was capable of adapting to different pH environments. And after we conducted we set it to 2 different pH environments, 7.4 and 8.5. We were able to see there was a negligible difference between these 2 pH environments for our CRP concentrations. It is crucial to prove that our sensor is superior in some senses in comparison to pre-existing sensors already in the market. And in order to do so, here is a table where we gather some aspects that we took in highest regard. The substrate material we utilized was paper, which enables a higher flexibility and adaptation to wound dressings. Another important feature was the limit of detection. And although some previously reported sensors have a lower limit of detection than our sensor, their linear detection range does not fall under the wound spectrum, which is, if we recall, 8 milligrams per liter. In summary, we were able to test for our initial biosensor and successfully detect CRP levels. In order to conclude our project of developing a complete smart wound patch, the next steps included would be to test for remaining 3 biomarkers, test with human wound fluid, enable monitoring, diagnosis, and efficient treatment of wound in one device, and test the product in a clinical setting. Thank you so much for watching this presentation. And now I'm open to any questions you might have.